I'm saying I'm going to use 2 points to get the question. For the action method, the second point is T25. So for the action method, yeah, I'll draw again. I'll draw one more going down. So here is the full delta y. Now if I'm going down, remember we start from the beginning, so 0.25 delta y is here. So going this way, that's T25, 0.75 delta y is here. So here is T75. So, for T25, I must have what? I want y prime to be equal 0.25 delta y. So I must have 0.25 delta y equals k delta u times what the model gives me, but now in the model I have times 25. Clear? Same equation I had before. Before I had T75, and T75 was matched with 0.75 delta y. T25 is matched with 0.25 delta y. If I was doing T57, I would be matching that with 0.57 delta y. To match a point in the model exactly with an experimental point, I would use the experimental measured time here and the experimentally measured y here. With the experimental measured y, is characterized as 1% of delta y. How are we doing? Are we totally lost or are we okay? Megan? I'm sorry, Megan? Here, Megan. Megan, are you smiling because you're lost or because you're okay?
No,
Megan? Mohammed, okay? So, and we're going to do exactly the same algebra. This is going to be equal to delta y. So this cancels this. And then I move the exponential to the other side, e to the minus t25 now, minus t naught plus d divided by tau equals 1 minus 0.25, which is 0.75. Proceed the algebra exactly the same way. Taking the natural log, minus t25 minus t naught plus d divided by tau equals ln of 0.75. I made a mistake here. Let's see. I made a mistake here. Okay, so I have an extra bracket 11. And the bracket should be here. There shouldn't be a bracket here. The bracket should have been before the division by that. Okay. So move the tau to the other side. You get minus t25, and I'll combine it with the minus t naught. And then minus minus makes plus d equals tau ln 0.75. And then moving this to the left, moving this to the right, you get an analogous equation to that has d plus, minus ln 0.75 tau equals t25 minus t. All this equation. Now I have two equations for two unknowns, and they're linear equations. So, one thing I can do, I can subtract them, and then I eliminate d. I have an equation only for tau. And since T75 is bigger than T25, let's take 1 minus 2. So if I subtract equation 2 from equation 1, All right, what do we have? So, d minus d cancels out. I have minus ln 0.25 tau. And from this I get minus minus plus ln 0.75 times tau equals d75 minus d naught minus d25 minus d naught. The d naughts cancel out. We can combine these two as tau times ln 0.75 minus ln 0.25, which is the length of the ratio, equals d75 minus d25. And of course, that's a ln of 0.75 over 0.25, which is the ln of 3. So you get that tau is equal to d75 minus d25 over ln of 3. Which I believe it turned out to be 1.1, let me look at my notes, times no, it's over 1.1. So that's the same, in my notes I have the result. That's d75 minus d25 over 1.1. We got tau. How can we get d? Well, use any of those, either equation 1 or equation 2 for d. If you use equation 1, now we have found tau. We can use equation 1 and get d equals d75 minus d naught plus ln 0.25. And that's how we get tau and d using the exponent. So, does it make sense? So we do the experiment, we get a step change. What I need to measure for my experimental data is t75 and t25. I don't draw a slope line for them. And then using this analysis, I find that tau is determined by this equation, and d is determined by this equation. There is a potential problem, though, with the three-point methods. And the problem is the following. I still have 20 minutes, or I still have 20 minutes. All right, good. So, the potential problem that we can have is, in some cases, some sigmoid curves may result in that method having a d that is negative. A negative delay can never be accepted. That would indicate that the system started responding before the input changed. Crystal ball. I know the flow of the coolant is going to increase, so I'm going to start dropping ahead of time. So obviously that's unacceptable. So in some cases, three-point method will give you unacceptably small delays. And also, even if it's not negative, if it's very small, that has bad consequences for controller tuning. So what I do, I use three-point method and slope method. And if the delay of the three-point method is comparable to the delay of the slope method, I will choose the three-point method. But if the delay of the three-point method is much smaller than the delay of the slope method, I'll take the slope method. Slope method is guaranteed to give you a good delay. Obviously, three-point method has the potential of being an even better fit, but has that potential pitfall. Yeah.
So the three-point method is not reliable.
It's reliable most of the time, but in some cases, it may give you a delay that is too small. So I wouldn't blindly use the three-point method without checking if the delay is okay or not.
Are there any telltale signs for just looking at the graph that it might not work?
If you see that the higher time is much, much longer than the first time, that's an indication that you may be in trouble. Depends also on what times you have chosen. Smith-Corrigan method is exactly the same, but uses T63 and T28. I would like to do that. And as you see in exams, I may ask you to use a 3-point method that uses T8 and T30. I can pick any 2 times, it's exactly the same method. You just simply change the equations accordingly. All is matching the 4-star equation to the experimental data. And in this case, you don't have to worry about not drawing a good slope line. Okay, but that's how. Now, I will give the Smith-Corripio method, but I can actually give you now the very first controller tuning method. And as I mentioned, first order plus time delay is very, very important because it fits the majority of practical applications. So methods have been developed that are essentially plug and chug once you have found K, tau, and D. And one method, actually I may not have brought it here. I may not bring the, I may have not brought the notes. I guess I'll wait until next lecture because I didn't bring my notes for that. But next lecture, bring your computers, guys. We are going to tune a controller. We're going to tune a controller and then play the game and see how well our controller is. Okay, so you're going to be tuning your very first controllers on Monday. So we are getting there. I know a lot of math stuff, but I hope you understood this. I would like to go also the Smith-Corripio method, and also other variant that you have seen from that you see from all the exams is to use the slope method for getting D. Instead of matching T63, match another time for tau. You can use D from slope and T50 for tau. There's nothing specifically magic to use T63. T63 is a direct replacement of the T do not use, but there's nothing specifically magic for it. Okay, how about the Smith-Corripio? Smith-Corripio, I'm giving the name, I haven't seen it elsewhere, so I'm giving it in the Smith-Corripio book from its first edition. It uses T63 and T28. So, for T63, we already did it, but for T63 I must have 0.63 delta y equals K delta U, which is delta y, times 1 minus e to the minus T63 minus T naught plus D, all that divided by that. And T28 must have 0.28 delta y equals K delta U, which equals delta y, times 1 minus e to the minus T28 minus T naught plus D divided by that.
I have a quick question.
Yes.
Is this method 4, or is this just a...
No, it's all method 3. 3-point methods, I consider them one method. Method 4 is with Excel.
Okay.
So this is method 3.1, 2?
Okay, method 3.2. Right. You can use any 2 points to match. Here I'm matching 63% with the East stated 28%. Pick any 2. Obviously, you don't want to pick 24 and 25%, okay? You have to pick points far apart. So, let me do the algebra a little bit faster. This one, you can say that I will get, after I take the ln of this, I will get minus T63 minus T naught plus D, all that over tau, equals, and you have a ln of 1 minus 0.63. Similarly, this will give me, and this minus is on the entire thing, okay? Minus T28 minus T naught plus D of tau equals ln of 1 minus 0.28. And if we manipulate this, we're going to get D minus ln of d from here, right? Minus means plus d, minus ln of 0.37 times tau equals t63 minus t naught, and this will give me d minus ln of 0.72 tau tau equals 228 minus t. All this 3, all this 4. Subtract 3 from 4. Sorry, subtract 4 from 3. So 3 minus 4. So we will get d cancels out, and we will get that ln minus ln 0.37 plus ln 0.72, all that times tau equals t63 minus t28. Okay, and so that will give me that you do the algebra, the tau is t63 minus t28 divided by
1.9. 1.9.
or times 1.5 times 1.5. So 1.5 times t63. It's easy to remember that 1.5 times t63 minus t28. And then you can get d from, let's use the t63 equation. D is equal t63 minus t naught plus ln 0.37 times tau. And what do you think is ln 0.37 equal to? That's minus 1. Because this is the equation that we know that when we have d plus tau plus t naught, d equals t63 minus t naught minus tau. Did we show before that t63 is d plus t naught plus tau? So you get back to the equation, which we got in the slope line. Slope line, how do you do? Remember, slope line calculates tau equals t63 minus t naught minus d. Same equation. Slope line uses this equation to calculate tau. The Smith-Qualico method, after you calculate tau, uses the same equation to calculate it. Okay? So this is the practical way, and there's another way we're going to learn, and that is optimization Excel solver. So that's the other method that I want to do. And the homework I'll give you Monday, I'll have you to do the model for all different methods. I give you some simulated data, use all 4 methods, and draw in the same plot the results of all methods, and see how well the model fit to the experimental data for all 4 methods. The 4th method is going to be, instead, okay, we have 3 parameters. That means we can have only up to 3